Hello, this is Math 2270 coming to you from the College of DuPage during the summer of 2020, and this lecture is entitled Annihilator Operator. Okay, previously we saw that sometimes it's convenient to write differential equations like this, where d raised to the k is that, and sometimes we even talk about the operator being L, where it will represent all of this. And here we have then L operating on y is g of x. That is a non-homogeneous equation, and this has constant coefficients. Now, not only is the operator notation a helpful shorthand, but it is very practical because we can avoid the mind-numbing rules that are talked about in section 4.4 for the guess and check method. In this section and this approach is more elegant. There are no special rules. It follows almost immediately once we have found an appropriate annihilator for g of x. And you see, if we can annihilate g of x, we turn this into a homogeneous differential equation, and we are experts on those. So before investigating this, we do need two concepts. Just take these as facts. This is differential equation tradecraft. You can factor operators that look like this, and they commute. It doesn't matter what order you apply them. You can be quite casual with that. Okay, so now we're going to walk through an example. So we're going to be solving this differential equation, but it is non-homogeneous because this. Now the first thing I'm going to observe is if I write this left-hand side in operator terms, it will look like this. It is d plus 2 whole squared operating on that. And I make note that if I consider the associated homogeneous equation, where this is equal to 0, my complementary solution is given by this. And I get this because it is a double root. But now what I'm going to do is I'm going to start with this, and I am going to annihilate the right-hand side, and I'm going to annihilate the right-hand side by taking the second derivative. It will kill that, and the second derivative will kill that as well. So if I do that on both sides, I get 0 here, and I get this. But this is a homogeneous differential equation. We know how to solve this. We know the solution is going to be a linear combination of these things. These two come from d plus 2 whole squared, and these two come from d squared. So that is what I get for my particular solution. I'm going to take this particular solution, I'm going to plug it into the left-hand side up here, set it equal to the right-hand side, and see what I get. But this is not as hard as it looks, because I'm not really going to bother plugging this part in, because I know this is just going to give me 0. So what I'm going to do is I'm going to take the cx plus d, the leftovers, and plug it into there and set it equal to this. I'll do undetermined coefficients, and I will get this as my values for c and d, and then my general solution is found by adding the complementary solution and the particular solution that I just found. Okay, now that we've done one, let's talk about what this is. So if L is a linear operator, if L operating on f of x gives you 0, we say L is an annihilator of f of x. And here I'm telling you that basically we're reading our results about linear homogeneous equations with constant coefficients. We're reading them backwards. So, for example, and you should think about this as we go along, but the differential operator d to the nth power, the nth derivative, is going to kill off all of these functions. D minus alpha to the nth power is going to kill off all of these functions. And the differential operator shown here, and by the way, you want to think about this differential operator, and notice it's being raised to the nth power, but d squared minus 2 alpha d plus a squared, alpha squared plus beta squared really is the factoring of d minus z and d minus the complex conjugate of z. Think about that and you'll see. But this operator then, which is this thing, both raised to the nth power, annihilates all of these functions. And a special case is d squared plus beta squared annihilates both of those. So here's our approach. We find the complementary solution, then we operate on both sides of the non-homogeneous to annihilate g of x, the right-hand side. Now we have L1 and L, two operators stacked together, equal to 0. So we know how to do that, and we delete the solution to the homogeneous. Actually, you're diluting solutions terms that are duplicated there. You'll see those examples, and you take what is left, and this is a particular solution, you slug it into L of y, and then you match the coefficients, undetermined coefficients, and then you have the solution to the problem. Differential operators that annihilate a function are not unique, so it's just like least common denominators. You want to take the lowest one that will do it. It makes your life easier. Okay, so here is a problem for you to dig in and doing this. You know what to do. And I'll see you in 18 points.